So I want to talk about silicon photonics and what's driving the field in particular, and about laser integration on it. And people like Steve and Ted Norris and others put down some of the lasers because they're really noisy. I want to talk about making really quiet lasers when you integrate them on silicon. And so there's some hope for us being legitimate laser scientists. So I do want to acknowledge Kerry Valhalla and David Plant, Lin Chang and Xinwan, which I've had a lot of collaborations with, and the other members are members of my group. Professor Liang has a copy of the slides if anyone's interested. I will talk fast, and if you have any questions, just raise your hand, and if I ignore you, shout them out, and I'll acknowledge it. And I am looking to hire postdocs. If anyone's interested in coming to Santa Barbara, we're definitely looking. So I want to first talk about the big drivers for silicon photonics. Dee and I were at the Optical Fiber Communication Conference last week, and there was a huge amount of excitement there. And it's all coming from data centers, as we'll see. And the top 4 hyperscalers are all spending $75 billion each to build out their, this year, data centers. And so this was the biggest OFC conference since 2000. And I want to sort of convey a lot of what all those groups are doing. I'll primarily just focus on work that's research with lasers integrated, just because the field itself is so big. So I'll talk a bit about comb generation to get lots of colors of light to get very high data capacity. And I'll talk about a few experiments at the end that use silicon photonics, going up to the most recent stuff at 58 terabit per second. And again, I'll talk about narrow linewidth lasers in particular. So here's one example. This is a bunch of rings that we use to generate combs of light integrated with arrays of either DFB or DBR lasers. And so that's sort of the level of what we want to talk about. So silicon photonics is still growing very rapidly. It started a long time ago with Richard Soreff, who said, silicon really might be a good photonic material. Of course, all of us said, no, it isn't, because it doesn't laze, and there's no electro-optic coefficient, and things like that. But he had a lot of foresight. It's a very good waveguide, and we can integrate everything else on top of it. And so it continues to still grow very, very, very fast. But again, I'll only talk about the small fraction of those papers, which is really involving laser integration. The big driver for it is any high volume application where cost really matters, right? And you need to get very low cost. And so these are certainly 6 such areas. I'll primarily focus on datacom, telecom, because of the big volume, dollar volume. Other things like LiDAR and having scannable beams, that's certainly, a lot of people are working on that, and that may still happen. And things like optical gyroscopes, because the loss in optical waveguides can be small, similar to optical fibers. Get performance close to what you can do with a fiber optic gyroscope. This is the driver. We all know how fast AI is growing and the demands it's putting on data centers and causing them to do this very rapid build out to much higher capacities. And so again, the growth of this, as we all know, is much faster than the performance of any of our chips. And so that's really been the stressor on this. So again, here's on the top, high performance computing. We all know it's doubling every 2 or 3 years, whereas the speed of interconnects or the speed of memory is a lot slower. And so the end result of that means we need to get many more lanes of traffic getting onto these chips. And so that's shown here versus time. As bandwidths go up, and we'll talk about where we are today. We're at 100 terabits today, basically. And since the electrical speed is getting phenomenally high, right? We're now talking about 100 gigabaud, maybe 200 gigabaud, but still a small fraction compared to 100 terabit. That means then you need lots of lanes, either lots of wavelengths in parallel, lots of parallel waveguides, and that basically just drives photonic integration. So there's lots of chips being made today that have literally 1,000 photonic devices integrated together to get to 1,000 lanes, right? You need 3,000 devices, right? A laser modulator detector for each of those lanes. So this again is just a structure of a data center, and so again, most of the interconnects within a rack are all copper today, and that's what silicon photonics is really driving towards, right? Is replacing copper. The problem is copper is very inexpensive and works well up to sort of 100 gigabit per second. But now we need to get onto a chip, 100 terabits, and that really takes us away from copper. Plus, the distances here, even within a rack, but certainly between racks and around here, hundreds of meters. You can't do that with copper. So photonics is really, everything from here up is all photonic today. And again, these capacities links needs to be a lot higher, right? Everything is really communication limited very much today. So we're both talking about scaling up as well as scaling out and getting to, literally millions of GPUs. So the copper problem is here. We're today at, all these interfaces are 200, 400, 800, 1.6 terabits. And copper loss at 200 gigabits is, over 20 dB. And just to get from the die out to a card. And so that's really pushing photonics getting in here. And that's really what we'll talk about today. Here's the way that has been evolving. So traditionally, it's all been based on indium phosphide PICs, DFBs, maybe arrays, DFB modulators, arrays of them. And a lot of data centers have been based on gallium arsenide VCSELs. But really, silicon photonics of late has really become quite dominant. And these still work for shorter distances, and they haven't gone away. But as we get, every 2 years, we've got to get another factor of 4. And so that really is driven this. And it's really the fact that we've got this electronics, photonics that have to be intimately integrated that really has driven the transition from indium phosphide or gallium arsenide onto silicon, right? Because everything has to be done on 300 millimeter wafers, all the photonics, all the electronics. And so that's what's really driving the transition. So this is a Broadcom chart. So it just shows what's their switch capacity versus time. And they follow this very rigorously for a very long time, doubling every 2 years. And so today the chips are at 100 terabits, and I'll show their latest chips. But in just a couple of years, we have to be at 400 terabits. And so, to get 4 times as much data in sort of the same size means they have to be a lot more efficient and a lot more dense. And that's what's really driving the field. So that's driven us from pluggables at the end of a circuit board to basically 3D chips where the electronics photonics are intimately connected. So this is the same information in a slightly more different way. We're moving from pluggables at the edge, front panel with chips and electrical connections, to optics initially on the board, but closer. And so that's onboard optics, to now putting the optics inside the package. And that's really where we are today for the most part. So you've got one circuit board here with electronics, photonics all around it. And then we're headed next is here. And so this is Broadcom's 50 terabit chip. So all the optics are in here. Now you've got to work out ways to put pluggable optical fibers on there and things like that. But that's all been worked out. To here, this is an Intel vision, but now the photonics, electronics are very intimately integrated, right? And by having you can't hit the powers necessary with this approach. You just can't. There's too much capacitance. Driving those capacitive lines takes, literally more than 10 kilowatts of power on that one package. Not workable. Once you head here, now you've got a few microns between the transistor and the modulator. And so there's no 50 ohm transmission lines. It's just a very small amount of capacitance. In fact, the capacitance of through silicon vias is too high at 200 terabits. So this is just very, very, very short interconnects. And at some point, you'll have this 3D co-package with integrated lasers. And Intel's doing that today, but they're the only one that's gone that far. So what does this mean? It means a bunch of things. We've gone from just 100 gigabit transceivers a few years ago to 3.2 terabits today, right? So at OFC, there were probably, 20 vendors of 3 terabit transceivers. So, this factor of 32x in 4 years is just mind-boggling to me. I would have never predicted that. And if you look at the power requirements, we've gone from 30 picojoules per bit down to 8 picojoules per bit, and now we're down close to just 1 or 2 picojoules per bit for the next generation chips. So again, even so, we're talking about many kilowatts of power out of just one of these packages. And so it requires water cooling, so everything now is water cooled, and that's actually really good for lasers and really good for silicon photonics. Lasers obviously don't work well at high temperatures, and everyone's always complained about, you can't have the laser in that package because it's way too hot. Well, now that you've got this liquid cooling there, and in fact, the liquid cooling goes directly on top of the PIC, that means the laser is actually fairly temperature stable. And the new standards have actually much smaller ranges of temperature. It's really good for silicon because silicon is very thermal optic, and as you change the temperature of that, the resonance wavelength of these rings changes a lot. But now that you have liquid cooling there, the temperature range is actually much smaller. It's much less of an issue. So the standards for lasers had to operate from 30 to 90 degrees C, and now it's, I think, 30 to 50 degrees C in the latest things that are coming out. So there's been a lot of change that's actually beneficial for photonics. So again, here's one announcement. This is what Broadcom showed. And so this is somewhat of a marketing slide, but they've gotten a lot of pushback. They've talked about this co-packaged optics. We're going to put, inside this rather large package, this 100 terabit chip is here, and around the outside are all these 3 terabit transceivers, basically, around it. It's all water cooled, and then the front panel of that whole thing is just optical fibers now, not either electrical cables or plug-ins. And they've been talking about it for a while, but it hasn't really happened yet. So as you can see, last year it sort of grew, but now they're actually projecting rather rapid growth of these terabits. And again, everyone's using the same technology, right? Broadcom, Arista, Cisco, everyone. And so the whole industry is moving this direction. And again, the big point is that by getting optics inside there, you really reduce the power required to get all of this data on and all of this data off the chip. So again, this is a Broadcom marketing slide, but my point being that the type of optics isn't necessarily determined yet. And so they say they'll work with all these options. So they might be laser modulator combinations. They might be VCSELs. So it's a lot of options yet. The other big announcement from 2 weeks ago was NVIDIA talked about they're doing silicon photonics. This is the first time they really endorsed silicon photonics as what they need. So they've really been pushing, their NLink, NVIDIA Link for copper interconnects. And so they announced InfiniBand as well as Ethernet switches. But again, in their case, 200 gigabit per second, but using, again, silicon photonic modulators to get the data on and off those chips. And so that's generated a lot of excitement. Frankly, what they're proposing, what they're doing is pretty primitive, right? Compared to what I'll show and most where the industry is, it's pretty primitive. It's single modulator per fiber, right? And what I'll talk about is 832, wavelengths per fiber. But this is their first step, and they're growing. The other big announcement they made is that, of course, they're using TSMC for the silicon photonics. So again, there's lots of foundries that do silicon photonics, but TSMC is they're sort of a latecomer to the game, but obviously they're the elephant. And of course, NVIDIA is going to use them because all the electronics is made by TSMC. And so that's the other big excitement coming out of it. And again, they're doing all the same vertical integration of electronics, photonics, and again, just using copper bump bonding between those two. And so again, the field's moving extremely fast. And again, this is a little more detail on it, but again, they're showing the same thing. We've got an electronic chip with all the photonic chips around it, and then all these are plug-in fibers, right? So whole issue is how do you get all the yield high enough to make this happen? This is a review article that, again, these slides are available from D if you want. This is sort of looking at the industry, and in particular, I'll talk today about a couple different ways of doing it. One is we either have lasers integrated with arrays of rings, or lasers integrated with arrays of Mach-Zehnder modulators, and I'll show both examples. And it's not clear yet which will end up dominating. One thing which I don't think is true anymore is that they have this reflection control here. So again, we know lasers are very sensitive to reflections, and it's very difficult to integrate isolators into PICs. And so there's two solutions to that. One is to have the laser injection locked to a high Q resonator. That makes it reflection insensitive. Or using quantum dots is reflection insensitive. And I'll talk about both of those. So other than that, I like this figure. And then that roadmap also talks about all the different ways you can modulate the light. I won't really talk about that very much, just for lack of time. In particular, the work we're doing uses two things. Either it uses arrays of rings, and we're doing that to get very low power, just sub-picojoule per bit sorts of powers. Or we're using slow light modulators, and we can get up to about 400 gigabit modulation out of one modulator that way with slow light. And again, so those are arrays of modulators. And so I'll talk a lot more detail about the systems experiments later, and that's really all I'll really say about modulators. The problem with lasers, as you're all aware, is that silicon is indirect bandgap, and so you need. People do talk about silicon lasers, silicon germanium tin lasers. My comment on it is simply that they're not efficient enough, right? When you've got 200 terabits of data you've got to generate and take off, the lasers have to be very efficient. And there's no way that an indirect bandgap will ever be used in these applications. So you can make a silicon germanium laser, but it will not be used for these applications. When you have a group 3-5 material, it's literally 100, 1,000 times more efficient. And that's any direct bandgap material is what you would expect that to be. So the issue is, how do you get these direct bandgap crystalline materials onto silicon? And there's sort of 4 approaches people use. So the least technical one, which is also the most common yet today, is just an on-chip laser. You've got an off-chip laser, it's fiber coupled. You get away from all the issues of reliability. If the laser fails, you plug in a new module. You don't lose the whole complicated co-packaged optic module. But now you end up having a lot of fibers going into these chips, and getting that high density is an issue. The other approach people use is just to have what I call hybrid integration, lasers and PICs close together. And I'll show we do a lot of that, a lot of examples, but it's only sort of one step getting to here or here. And in here, we're bonding 3-5 materials onto SOI, silicon photonic wafers, and we etch off the substrate. So there's no, the alignment is very coarse. You just have to have the gain material where you need it. You use all the mask alignment after that to fabricate the lasers and the rest of the silicon photonics. So this has been commercialized by a bunch of companies, Intel and HPE and Juniper and others. The last one I'll talk about is epitaxial growth of 3-5s in silicon. And that's made a lot of progress, and I'll talk about that. But it's not yet commercially viable. So we don't yet have performance that's acceptable. So these 2 approaches are sort of what people are doing today. So by heterogeneous, we mean taking a silicon substrate. So it's all processed in 300 millimeter wafers. You have all the advantages of a modern 300 millimeter fab. And you may have, say, nitride waveguides, which have very low loss, literally 0.1 dB per meter. And you can make resonators with Qs of 400 or 500, maybe a billion. You can combine it with aluminum gallium arsenide, and so or lithium niobate for that matter, thin film lithium niobate. The advantage here is that it's clad in SiO2. So you get very tight confinement of the mode inside these very thin algas layers and very narrow widths. And that gives you very high nonlinearities, basically, and we'll talk about that. And then using silicon waveguides and maybe YIG, if you need isolators. This tends to be not very integrable because you then need a magnet to magnetize it, but we have demonstrated, and others have done it as well. Silicon modulators, and then ways to integrate gain on top of here. And so if this is on top of silicon, it could be indium phosphide. If this is silicon nitride layer, it could be gallium arsenide or gallium nitride. So we have looked at making heterogeneous PICs as short as about 440 nanometers and as long as about 5 microns. And then maybe germanium silicon modulators and detectors. So trying to combine all of these together is what we mean by heterogeneous integration. So I want to acknowledge Dee here. When we first started this back 2005, he worked on how do you get good bonding of 3-5 to silicon. And it's all based on oxygen plasma enhanced. And Dee noticed that when we were making these lasers, when we etched these waveguides, these gaps next to them, there weren't any, you had very good bonding. Everywhere else you had bubbles and these thin micron thick films would not work very well. So he patented that, and actually Intel licensed it, and they've used it to make in their 300 millimeter process. He was also instrumental in scaling this up. We were all doing 1 centimeter, and he scaled it up to 6 inch. And today Intel does this on 300 millimeter wafers. So it's come a long ways. One advantage when you bond materials is that you can bond multiple epis at one time. So you'll see this in the next slide from Intel. They've done this from the beginning. They do CWDM, and for each PIC, they bond 4 different epis to get wider than you can get with the wavelength range of a single epitaxial material. And so they're going, in their case, across 80 nanometers. We did even further. So this is now combining from O band, E band, and then SC and L bands, all in the same PIC, right? And so in Intel's case, they take a 300 millimeter wafer and they place all of the die, and they may have, and their standard process is 4 different die, and then you bond all, say, 5,000 at one time, etch the substrate off, and you do all the processing together. But that's the advantage of heterogeneous bonding. You combine lots of different epi together. It may be laser epi with modulator epi with detector epi even. So I've got a couple slides just to show what Intel's doing, because they're kind of the behemoth here. They've taken this technology. It's on a 300 millimeter process in a fab that primarily does electronics. And so again, just like I've shown here, you take this handle wafer with all these die on it, you flip it on here, etch off the substrate, and do all the processing. As it says, no critical alignment, low coupling loss. So the laser, if you try and do hybrid bonding, you solder a laser close to a PIC, it's hard to get less than a dB loss in there, and you get reflections. This, it's much better. We get down literally below a 10th dB. The other nice thing is you can use known good die when you combine it together. So as it says here, they've now got 32 million lasers in the field. And these lasers are good lasers, right? We're not talking, these things laze up to, this is 140 degrees C. So that's beyond what, and that's partially because silicon's a very good thermal conductor, right? So it's better than indium phosphide. And good wall plug efficiency, 25, 24%, which is important to get, the power down to where you need it to be. But this is the real winner. And this is, I don't think any of us anticipated this at the beginning, but the reliability is really good. The reliability is phenomenally good. So this is the reliability of a conventional, the best quantum Hall lasers Intel have procured over the years. And this is now based on tens of thousands of lasers. And so, if one laser, that's a 10 fit. So 10 failures in 10 to the 10th hours, okay? The Intel lasers are down here 100 times better than that. And part of the reason it's more reliable is that there's no exposed 3-5 facets. So everyone making indium phosphide lasers or gallium arsenide lasers, facet damage has often been the issue. But now everything is buried underneath SiO2. And so none of these transceivers are hermetic, whereas most indium phosphide packages have always been hermetic. None of that's done here, right? Nothing's hermetic, but the reliability is much better. And as it says here, so they've had 41 billion hours, device hours, and it's if you notice, this is, let's see, yeah, they have 4 times as many lasers as modules because they have 4 wavelengths on. Their biggest product has 4 different wavelengths on there, CWDM. But in these 45 billion hours, they've only had 2 laser failures in that time. So it is much more reliable than any of the other structures. And so, again, all the different hyperscalers have this kind of data because they're now based on millions of transceivers. We've also worked with Tower Semiconductor and Quintessent. I'll show a couple slides in Quintessent. It's a spin out of my group that I'm involved in. And in this case now, the difference is these are quantum dot lasers, and I'll explain why quantum dots in a few slides. But again, this is a standard foundry process now that Tower's offering, and they're now shipping these devices to multiple customers. I'll skip this. But Quintessent is all about WDM. How to get the high capacity, lots of lines. Let's do that with lots of colors of light. And so this is one chip that puts out hundreds of lines. At 100 gigahertz spacing, there's typically 8 lines. They're trying to go to 16 or 32. And you can get these sources with very, very low RIN, very low noise, which is important. So this is their vision, and this is what one of the dominant approaches people are doing is you have lasers integrated with arrays of modulators. So each modulator has a slightly different diameter, so it resonates at a different wavelength. So you don't need to split the light out into independent colors, modulate it, but rather it's one laser just feeds all these different modulators at a time. So everything's now has been, everything's silicon photonics, but silicon photonics with silicon waveguides. We do a lot of work on other materials. either compound semiconductors on insulator or silicon nitride. And the advantage of silicon nitride is this, that the losses are, tenth dB per meter, so much less than silicon, much less than gallium arsenide or indium phosphide. And that allows us to make higher Q resonators, which allows us to make better lasers, lower noise lasers in particular. And also lets us work into the visible. So even at 400 nanometers, this is actually much higher. I think now the field is kind of down here more like 12 dB per centimeter. But you're getting into that range where silicon nitride and silicon oxide become absorptive in the blue and UV. But if you make it with nitride, this is another spin out of my group, Nexus Photonics, and they're trying to make lasers from 1550 into the visible, and so you can see a bunch of tunable lasers at a variety of wavelengths. And again, you have to use different epi to do that, but that's all been worked out. And again, it's in a standard foundry process. They don't make anything themselves. They're fabless. But you can see some details of what a wafer looks like with a lot of different devices on it. But this is the takeaway for me. If you look at the yield, and this is not uncommon, maybe 100%, and this is the variation here is just a couple of milliamps, and so far better than we ever get with silicon photonics at UCSB. But again, you get into a modern fab with good lithography, and TSMC is the best example of this. If you look at their data, their devices are so incredibly uniform. It's way better than you get from AIM or Tower, or certainly UCSB. It's really impressive with what good lithography gives. This is an example of coupling one of these lasers to rubidium and sweeping it across the rubidium line. So again, atomic clocks is one application, and again, the line widths of these lasers can be very small because of the high Q of the silicon nitride, which is what is important. So let's talk about narrow line width lasers.
Why do you need the narrow line, which is I understand?
Why do you need it? Well, like some of the atomic transitions are very narrow, but the other one we're doing here is to make microwave oscillators. The driver for our project is microwave oscillators. And you can now make an optically based microwave oscillator that's 20 dB, 30 dB better than your best Keysight oscillator. And that's just because the Qs we get optically are so much higher than you can get with microwaves. So this just looks a line width over time of lasers, and the red are indium phosphide lasers. They've gotten better, and the best lasers are quantum dot based, because the line width enhancement factor, quantum dots can be 0. So again, the Shallow Towns line width has this 1 plus alpha squared. If alpha is 0, that's better than indium phosphide, where alpha would be 4. But once we couple the silicon, you do much better. And so this has really been going on the last 10 years. And these are now Lorentzian line widths down to about 40 millihertz. As you'll see, this is nowhere close. We can do much, much better. I berate my students because they're more than 10 times worse than they should be. So we have to do better. But anyway, this is just classic Shallow Towns, and one way to write it is versus Q, and it goes like 1 over Q squared. So the higher Q you get in these cavities, of course you get narrower line widths. It's not a surprise. So this shows some of our work over the last 10 years, and so line widths have come down from hundreds of kilohertz down to, say, 100 hertz. I'll show better results in a second. But this is just for an integrated laser cavity. And the main reason is not the evolution of structure, although I'll talk mainly about these two structures, but mainly just that the loss in silicons come down. So Qs goes up and the line width goes down. So our standard workhorse for all these things, visible to infrared lasers, has 2 rings, and the rings have slightly different diameter. And so the light comes in, goes around both of these cavities, comes back out again. And then you have a gain section, a phase tuner, and then on the other end we have a loop mirror. As you change the kappa of this coupler, the output coupling goes from 0 to 100%. And so it's really nice just to have a tunable knob there that allows you to change how much power you get out. And obviously, high power out also means more noise in the cavity. So there's a trade-off there between noise and power. So what we're doing is just this. We have 2 rings, different diameters. So they line up at 1 wavelength. They get successfully offset. And then eventually it comes back in phase again, right? And so depending upon how different you are, changes the space and how close this one is versus where this is. So we want this other line to be outside the gain width of the material. So we push that out where the laser, we don't want it to laze at this and this wavelength. It needs to be single wavelength, right? So it's much like an SGDBR, if you're familiar with that approach, but rather using gratings, we're using rings. We get much higher Qs with rings than you get with gratings. And so this works better than that standard tunable SG2BR approach. So if you look at the composite mirror, it looks like this. And again, you need to suppress this enough that these lines don't laze. And so there's a lot of design that goes into it. But here's an example. This laser tunes across 40 nanometers, has reasonable thresholds and powers, and a very clean tuning map. Whether you tune one ring or the other ring, you can tune across the full 40 nanometers. But it's very predictable, very reproducible, and that's what you need for real products. You can do better with 3 rings, and so this is a picture of what that looks like, and so you can get better suppression of these close in, and you can push these further out. And the end result is you get wider tunability and narrower line width as well. And that's shown here. So this is a picture of what the device actually looks like. So the 3 rings are a little hard to see, but it's not too big. It's maybe 2 millimeters by almost a centimeter. That's a fairly big die. But now you can tune over almost 120 nanometers. That's a lot for one gain region. But it has low RIN and then fairly low line widths, about 95 hertz for NCN line width. So again, I'm talking about the high frequency line width out here at higher frequencies. Now these don't tune continuously very far. If you go very far, then you get a mode hop of that cavity. And the main design thing, if you want to get maximum tunability, continuous tunability, is to make the whole cavity short. And so shortening up this thing is what matters. And the biggest we've seen is about 375 gigahertz. So that's not a very good number. If you have an external grating coupled tunable laser, you're used to something that's much larger. But that's because as you tune that external grating, the number of wavelengths in the cavity doesn't change. But at any rate, that's what it is. So how do you do lower? Well, we have to go from silicon waveguide, that's what that was, to silicon nitride waveguides. And then we'll start using injection locking and then locking to high Q resonators to get really narrow line widths. So this is some work with Kari Vahala. So here's the silicon nitride rings here, and then here's the laser coupler. So this is hybrid initially. We're now doing heterogeneous, everything integrated together. What you see here, this is the noise, frequency noise out of a standard DFB laser. It's about a megahertz line width laser. That's about what you expect. But when you couple it to these high Q rings, so it self-injection locks. This gain region injection locks this high Q cavity. And the longer you make the cavity, the larger the volume, and the lower the thermal refractive noise. And so this is a fairly short cavity. This is I think, a 1.4 meter cavity down here. But you get about a 70 dB reduction in the noise. And so that makes a big difference. If you making any kind of sensor that is making measurements in the megahertz region, this really is, it's real. The noise out of this laser is really 70 dB lower by coupling it to this high Q resonator. So this compares the frequency noise in the black here of, I think, one of the best fiber lasers. So again, they're long cavities. They tend to be quiet lasers. We use them in the lab all the time. But these lasers are now almost 20 dB better at a megahertz because of this high Q silicon nitride cavity. The other we've been doing is, normally when you want to make solitons, quiet solitons, you have a laser pumping a resonator of some kind. There's a lot of different resonators people use with an isolator now to stabilize the cavity. But it's hard to generate single solitons, right? To get a low noise comb generation has to be a single soliton. Multiple solitons, is too noisy. So you have to typically tune the power and tune the frequency just right so as to get it into the single soliton mode. It's kind of painful. It takes a PhD. But if you do this direct pumping, we call turnkey generation of solitons, there's no isolator. We can't integrate it with an isolator, so we had to go that way. But it turns out the backscatter from this resonator locks the laser, self-injection locks the laser to this ring. And you get single solitons every time. So whereas this process is not guaranteed, this process, when you turn it on, it goes directly into the single soliton low noise mode. And that's what you want for all these applications. So now you can generate combs of frequencies. And this is a fairly long cavity, a 20 gigahertz comb. This is a shorter cavity, a terahertz comb. But again, you get nice soliton, low noise solitons out of it. And so we use this for a lot of things. Oh, one minor thing is we now use multiple rings together. So if you use 3 rings in particular, I can tune the dispersion of that thermal cavity to be either positive or negative. And so initially we're using these to generate bright solitons, but now we can, in the same device, generate bright solitons or dark solitons, either positive dispersion or negative dispersion. And that's really pretty interesting. So this shows sort of where we should be. We are today at 0.1 dB per meter. We routinely get that out of 2 different foundries. And at that point, we should be at roughly 1 millihertz line width, Lorentzian line width out of these lasers. And so today we're about 40 millihertz. So we're up here somewhere. But everything fits this line pretty well. We just have some excess losses in the cavity that end up making it worse than it should be. You can go further, and so we're locking these now to high Q resonators. And so these are made at Yale and at NIST. And so it's a collaboration, again, with people at NIST and Kerry Vahala. Peter Rakic in particular, I should be listing here. So this is the laser I've been talking about. So it's a gain region integrated with a grating for extended cavity narrow line width, integrated with a resonator, again, to get, fairly low line width. Now we lock it to this high Q cavity, and the end result is here. So the laser noise by itself is here in purple. When we lock it to that cavity, so again, it's just tuning it so it locks into the range, then we get, say 50 dB noise reduction. When we lock to this high Q cavity, we get another 60 dB of noise reduction. So this laser has an integrated line width of about 1 hertz, and, but you really do get 110 dB noise reduction at low frequencies. So I think for a lot of sensor applications, this will be important. We're using it for microwave generation, and indeed it makes a much, much more quiet microwave generator.
Excuse me, what is the stability of that frequency? I know that you can make it narrow. If you make the cavity larger, would that frequency be stable?
Well, this is time average. This is time average now. So it is not moving more than a hertz. It's staying within.
That's the phase noise, but let's say the size of cavity changes with temperature.
It does. Well, you can see that here. So here's the Allen deviation plotted. So this is 1 second here. And this orange curve is the drift of that cavity due to temperature fluctuations over time. And if we remove that drift, then you get good Allen deviation out to, say 10 seconds or minutes. But you're right, so you need ULE cavities and you need vacuum in that cavity. But Yale's now doing this, they're making wafers of this, right? So each wafer has, it's a high Q resonant, a DBR mirror on one side, ULE with a gap in there, and then another DBR cavity on top. And then if you evacuate it, then you get rid of any of the air perturbations. And that's about the best you can do. But they're making this at wafer scale, so they'll do dozens or tens, 20s of devices on a wafer at a time. Yeah.
What's the shallow Towns limit?
Well, that's fundamentally where this is coming from. That's behind this calculation here. But it is, well, way back where, here. So here's the Shallow Towns formula. We're putting all that, where the Q of the cavity, putting all that stuff into the quote Q of the cavity, which we can measure. And that Q is limited by thermorefractive noise. So, and there are better materials than what we're using, so that would give you lower thermorefractive noise. Okay, so, this is now, there's, yeah.
So with closer offsets, it's reducing the phase noise, but do you know why in the far offset it's increasing the phase noise?
So there's a, we're locking this laser now to this cavity with a PDH lock, and there's a limit because of the time delay in that PDH locking loop. So that's what this red line coming up here is that. So if we can integrate the whole thing and make it smaller, we can push this out to higher frequencies. And we've done some of that. But yeah, so, and this is sort of just the blue and the purple are just the shallow Towns limit, so high frequency limit of that cavity. Oh, so now we've been working on integrating it all together. So again, uses heterogeneous integration. So Chao Zhang was doing this in my group, and he's now at University of Hong Kong. So again, this is the same heterogeneous I talked about. We have silicon waveguides. with silicon 3.5 gain. We couple these silicon waveguides to silicon nitride waveguides, and this is sort of a redistribution layer. Then there's another layer that's down here that we couple from here down to here. So there's a lot of transitions. They're all adiabatic tapered transitions. So the design of that is important, and having fine fingertips is important. I don't know that you really need 2 layers. We were doing this because when we fabricate all the laser processing, we were degrading the Q of the silicon nitride. So we'd start with a Q of 400 million, and by the time we're done, in fact, these results, the Q is about 40 million. So we stopped putting them up here, and we buried them underneath microns of SiO2, and we're still seeing the problem. And it turns out that silicon nitride has a defect that is excited by UV light. And so when we're doing a lot of the laser processing, we're exciting this. And if you anneal it, and Joel Guo has a paper on that, if you anneal it, you can eliminate that. So you don't really need to bury this beneath 3 or 4 microns, but we were going down that path till we understood why we were getting the degradation in processing. So here's an example of that. So here's the silicon nitride. Here's the gain region right here. And one nice thing now is most of the cavity is silicon nitride, silicon dioxide, low thermal optic materials, right? So if you look at temperature dependence of this, it changes about 1/8 as fast as either an indium phosphide or gallium arsenide or silicon-based laser. And so what that means is you can now place them a lot closer together if you don't temperature stabilize. And you don't really need CWDM, which is important. And so again, this is the same thing I just showed you. Now the laser, phase modulator, resonator, they're all integrated together in the same chip. So this is all the same thing I've been showing you. The laser by itself has, actually this is the previous version. The integrated version of this is a little better, as shown here. And so again, I forget how many, 5 hertz in this case. And in this case, it's in the normal dispersion we see. Anomalous pulses if you drive it hard. This is one exciting thing about this. So normally lasers need isolators, right? We all know lasers need isolators. And that's shown here. So this laser right here, if you reflect light back into it, even at minus 40 or 50 dB, you see noise generated from that external reflection. So you need really good isolators for that. But if you couple this laser to a very high Q resonator, so this is the same device here to here, but here it's mistuned. The laser is not tuned to a resonance. Here it's in resonance. Now you see, even with basically 100% reflected from that facet, there's no noise coming back into there. That's really exciting. Basically, this very high Q cavity makes it impervious to external reflections. So you can send 100% of the output of this light back in, and you don't see any perturbation. So that's pretty exciting. And so that's what it shows here. You look at the frequency noise with basically very little feedback or high feedback. Minus 7 dB, that's our laser to fiber coupling back. So 3.5 dB each way gives us a total of 7 dB. So it's 100% reflection in the fiber. We still don't see it. And you can measure error rates in transmitters. We don't see any errors. Yeah.
So why is the red laser a big role here?
Why is the...
Why is the red laser a big role here? So
Well, just the Q is so high, right? You know, Q of, say, 100 million, that it just, the little perturbation of what, well, it's the little perturbation of what comes back through here doesn't have much. But actually, if you look, compare this one through and drop. So if you send the reflection back here, you do see some noise at about minus 10, minus 15 dB return. But if you take this port, it gets filtered by this resonator, and consequently you don't see anything even at 100%. So the fact that this resonator filters the light getting back into the laser cavity is what makes that happen. So we've been doing some other work. This is a collaboration with Lynn at University of Rochester on integrating lasers on top of Tiflin. So this right now is hybrid integrated. We now have versions where it's heterogeneously integrated on the same chip. And what we're trying to do here is generate a low noise, narrower line with lasers, but also we want to double in the same cavity. So we made the cavity resonant at the laser wavelength and make it resonant at the second harmonic wavelength. And all the same things happen. So this is, again, a Piplin resonator, and this is the noise of the DFB laser. And when you couple it to this cavity, you get the red light. Let's see. Yeah, the red light. And then the blue light, the doubled light, has virtually the same noise factor, although it's higher by 6 dB, as you expect, because you've doubled the light. The noise goes up by 2x, or 4x, 2 squared. So anyway, all these same ideas work on TFLN. And one of the things that Ming Shao and my group has done is to make these same things with, we're calling it a Pockels laser. So again, we put lithium niobate tuning of the frequency, basically, so you can make very rapid chirping up and down of these lasers and maybe use it for LiDAR and things like that. That's kind of the idea. So a lot of what we're doing is now just integrating heterogeneously lasers onto TFLN. So the last topic I want to talk about is basically, this has all been heterogeneous, monolithic epitaxial growth. So again, Paulab has done that, and he's done quantum dots a long time ago. So we're just following what he's been doing. And these are the 3 people in my group that have been doing this work. So why use quantum dots? There's a lot of papers that he's published on it. Our main issue is 2 things. One is the lower linewidth enhancement factor, and the other is insensitivity to defects. And so here's the result. This is why I would argue that if you're going to epitaxically grow lasers on silicon, they'll be quantum dot. So people have been growing lasers on silicon since when Steve Forrest was at Bell Labs and I were there a long time ago. And I was amazed they published this paper where the lifetime was only about a minute. I would never publish that paper, but they did. But today, the longest, even today, this is the world record today, is 400 hours for the lifetime of a quantum well laser on silicon. It's just because of the lattice mismatch, a lot of dislocations, the dislocations propagate, and the lifetime is terrible. With quantum dots, we're up to, at room temperature, 100 million hours. And so 100 million versus 400 hours. And so there's a huge difference. So our latest results actually got published earlier this week, I think on Tuesday. Sandia has been irradiating our quantum dot lasers with neutrons and gamma rays and things like this for space applications and nuclear applications, obviously. And they're about 10 times better than the best commercial quantum well lasers they can buy. So these are lasers we made in the lab at UCSB, lots of defects, but they're still 10 times more robust than the best quantum well lasers. And so Seth Fortuna just published that earlier this week. So this is why we like quantum dots. And we've done a lot of work on dislocation propagation in quantum dots, and it's the high indium content, because they're indium arsenide quantum dots, 100% indium, that prevent dislocations from propagating. It's a really interesting defect field. So if you look over the generations we've been working on, we started our initial lifetimes weren't very good, 800 hours, similar to the quantum wells. But we're now, the latest ones at room temperature are certainly 100 million hours. And even at high temperatures, they're over 1 million hour lifetime. So there's a lot of things you do, thermal cycle annealing, strain layer superlattices, p-doping. Turns out you need to put in dislocation blocking layers that when you grow on silicon, you may have low dislocation defects because of all these things. But when you cool it down to room temperature, the strain builds up enough to generate misfit dislocations. And you have to deal with that. And so that's what these latest 2 things do, generation 5 and 6, to get it. So that was the first reason. Other reasons, and again, Paul's written lots of papers, high CW temperatures, the highest temperature lasers are quantum dot, low threshold current, lower lateral diffusion, because we want to make typically small rings, and that's a lot of what Dee has been doing. Low linewidth enhancement factor, I put 0.5. You can see 0 in it, which makes it, so again, the reflection sensitivity goes like 1/alpha to the 4th power. So if you go from 4 of a conventional quantum well laser to 0.4, that's 40 dB less sensitive to reflections. And we've seen 0. You can get 0 if you want to. And then the other thing we do is get better mode locking because of the higher forward enhancement factor. So we've been growing these for a long time. Most of our work has been on planar growth. Most recently now, we etch these deep wells and grow all the quantum dots inside these wells. And we have to do that to get the lasing region lined up with the waveguides in the silicon photonics. And so we're integrating this with SUNY's standard silicon photonics process. And we're taking wafers that they have, all the modulators and detectors are integrated on there already. So again, it's 300 millimeter fab. We've transferred the growth to IQE. So if you want to buy quantum dot lasers, 300 millimeter wafers, they'll gladly sell them to you. And so here's the picture. I'll show some of these. But this is you can see the laser light here coupled to a silicon nitride waveguide. So again, we're growing these in pockets. It's a lot harder. Our Our processing is on smaller coupons, that's all we can do, but AIM is doing it on 300 millimeter wafers. And so you can see here, there's a quantum dot layer here, this is the waveguide, this is the pocket, and again, it's coupled then over here to the silicon nitride layers. So these are the latest results. See you, Steve. So reasonable Li curves. The fiber coupled light is lower. So again, we're losing coupling here is not nearly as good as heterogeneous. Heterogeneous, as I said, is 0.1 dB. This is more like 3 or 4 or 5 dB, but it's better than it was. So now we're making DBR lasers where the gain region's coupled to DBRs in the silicon nitride, just to say, okay, we do get enough coupling to make a external cavity laser. And we couple it with modulators then, and that's shown here. So these are coupled to 4 modulator arrays. And so again, AIM is developing this, and so everything is now on 300 millimeter wafers. So again, it's not really ready for prime time yet, but it's getting a lot closer. So we'll skip that. All right, so I've talked way too long. I'll just briefly talk about a couple of systems experiments that use these mode lock sources. And there's a lot of ways to make combs, mode lock lasers historically, or nonlinear devices. I'll talk about quantum dot devices or silicon nitride or aluminum gallium arsenide. And so we're making quantum dot devices, and people talk about magic mode locking with quantum dots, that they just, you don't even need a Satchel absorber, they just mode lock by themselves. And the reason is that the forward mixing coefficient is 10 times higher in a quantum dot. And that's theoretically predicted. Wang Chao did all the theory for this, and our measurements agree with his predictions. And what you see here is that this is a quantum L device, this is a quantum dot device. The forward mixing coefficient of quantum dots is about 10 times higher. That means that all the lines want to lock together. And that's good for making mode lock lasers. So here's an example. It's a mode lock symmetric laser. Each of the lines is about the same power, which is important. D makes quantum dot lasers and quantum dot ring lasers and coupling them with modulators. So I think you've seen all of his results at HPE in particular. But we've been working on gallium arsenide for comb. If either use mode locking, if you don't use mode locking, you want nonlinear material. And most people use SiO2 or silicon nitride. We've been using gallium arsenide because the Chi2 and Chi3 are much higher than lithium niobate or silicon oxide or silicon nitride. And so if you look at the threshold power to generate a comb, it goes like 1 over the nonlinearity portion of the area, so we make them very narrow, very thin. And we try to get as high a Q as possible. So these Qs are not as high as silicon nitride, maybe 2 or 3 million. But the end result is even with low power, you can generate combs of frequencies, even just microwatts of power. And so I'll just breeze through because I apologize, too many slides. One set of transmission experiments uses these comb sources with mode lock lasers, arrays of rings made at AIM, and we got it to about 1 terabit with about 0.2 picojoule per bit efficiency. Another experiment used the same mode lock symmetric laser comb to do coherent transmission. So now we have arrays of modulators, but we just need 2 lasers. So one laser generates this comb, the second laser generates the comb to down convert all those coherent signals, and we can get, again, flat combs and get 12 terabits of transmission. Another experiment, this was 2 terabits, we'll skip that. I'll get to this one. So this is work really done at PKU and Lin Chang's group. We supplied the comb source for it. Again, all these experiments are just doing the comb source. But again, getting up to 58 terabits. So this is a big experiment, right? 6 modes in this fiber, 2 polarizations, 34 comb lines, 32 QAM to get up to 58 terabits. But a thing that they really talk about here is that because we get this injection locking of this ring, laser and the ring together, they don't need DSP processing for the frequency fluctuations. And consequently, it reduces the DSP processing by a lot. They claim 5 nines. I hope that's really true. But the end result is getting rid of the frequency. Narrower line with lasers is really good, is really good. So to summarize, we are getting up to sort of VLSI sorts of photonic levels, tens of thousands of devices integrated together. Broadcom is kind of doing that. A bunch of companies are. The orange curve here is when you have integrated lasers. Green is just silicon photonics by itself. So, you know, it's the field's progressing. So I do want to thank the students in my group and thank a lot of former students for all their contributions. So sorry to be long. Be glad to take questions.